The reference material for this particular lesson on complex numbers and electrostatics, you'll find a chapter in the manual that's entitled Complex Numbers and Electrostatics, and later on we'll find a chapter that's labeled Direct Current Circuits. In the NCEES handbook, the relevant pages are as follows. For the material on electrostatics, it's on page 6. That's for the electrostatics part of it. You'll find the relevant formulas there. For the complex numbers, it'll be on page 69. Numbers 69, and when we get around to the direct current circuits, it'll be pages 66 and 67. So we'll put down here 66 and 67, but we'll save those until we get around to the DC circuit. So for now, for complex numbers and electrostatics, let's locate the chapter in the manual, and also in the handbook, turn to pages 66 and 69 for what we're about to cover. All right. On the subject of complex numbers, we define a plane, a complex plane, to have a real axis and an imaginary axis. And a complex number is represented by a vector in this plane. So if I have coordinates A units to the right, and say I have B units vertically, this would describe a complex number A plus JB. Some people use I, some people use J to indicate imaginary. And the vector representation would be a vector looks like this. It'll have an angle theta at this point. But let's forget about the angle theta for just a minute and look only at the components A and B. When we describe a complex number by A plus JB, it is said to be in the rectangular coordinates, and it's very simple. We just go to the right or to the left, as the case might be, along the real axis. Then we go vertically for the amount B, whether it's positive or negative, accordingly. All right, well, that's fairly easy. We will sometimes indicate that Z is a vector. It's equal to A plus JB, and it's described by its rectangular components. There's another way to describe a vector. Instead of talking about the components along the two axes, we can describe it by a length and an angle theta that this vector makes with respect to a reference axis. In this case, the positive real axis. So we would say that this vector has a length c, right, it says c, and it forms some angle theta with respect to the reference axis. So here's an alternate representation. The second representation we're showing over here is the vector form, more commonly called the polar form. And I guess the word polar is really the more commonly used expression. So you can describe the complex number either in terms of its rectangular coordinates or in terms of its polar coordinates. As an example, suppose A were equal to 3, B were equal to 4, then we would say that this complex number Z is equal to 3 plus J4. However, if we wanted to describe it in terms of its polar representation, we would say that the length of this vector, we can calculate that by using Pythagoras. If this is 3 and this is 4, then this length would be the square root of the sum of the squares, 3 squared plus 4 squared. It gives us 5. And 5 forms an angle, and if we check to see what that angle is, it's approximately 53 degrees. So 5 at 53, or 3 plus J4, gives you the same thing.